In this video, we derive these formulas for the multivariate Gaussian integrals, where this gamma is an n by n matrix that is real, symmetric, and positive definite, and X is an n-dimensional column vector. Okay, let's start. To begin with, we assume that you already know these formula for the univariate case. Here, gamma is a positive constant, and exponential of negative 1 over 2 times gamma x squared integrated over the entire real axis results in square root of 2 pi over gamma. And the first moment, so x times this factor integrated results in 0, and x squared times this factor results in this. So this factor times 1 over gamma. If you compare these formulas with the multivariate case, you see they are very similar. So for the zeroth moment, it's square root of 2 pi over gamma. Here we have square root of 2 pi to the power of n times the determinant of gamma inverse instead of 1 over gamma, because gamma is a matrix, so we can't just write 1 over gamma. It's a gamma inverse determinant. And for the first moment, it's the zero vector. For the second moment, so this is x is a column vector, so x transpose is a row vector. So this entire thing is an n by n matrix, and the result is this. So this one is the same factor as this one, and here we have gamma inverse instead of 1 over gamma. Here, 1 over gamma, here we have gamma inverse. Before moving on to the proof of those formulas, first let us review some linear algebra. So, let gamma be an n by n real and symmetric and positive definite matrix. Here symmetric means that gamma transpose is equal to gamma itself. That means the ij element of gamma is equal to the ji element of the gamma. And positive definite means that all the eigenvalues of this matrix gamma are strictly positive. Here is a theorem from linear algebra that is of great practical importance. If gamma is real symmetric, then we can always diagonalize this matrix like this, where this V is an orthogonal matrix and this delta is a diagonal matrix. Moreover, we are assuming this gamma is positive definite. So all the diagonal elements in this diagonal matrix, which are of course eigenvalues, are positive. And this matrix V is an orthogonal matrix. That means V times V transpose is equal to V transpose times V is equal to the identity matrix. Of course, the column vectors of this V corresponds to the eigenvectors of this matrix gamma. Here we note the following basic properties of these matrices. First, the determinant. We denote the determinant in this way. The determinant of gamma is equal to the determinant of delta, which is the product of all the eigenvalues. So these are the diagonal elements of this matrix delta. And the determinant of V is equal to the determinant of V transpose, which is equal to 1. And the determinant of gamma inverse is equal to 1 over the determinant of gamma. And the inverse matrix of delta inverse, is equal to a diagonal matrix whose diagonal elements are 1 over delta i's. So delta I is an eigenvalue. And the inverse matrix of gamma can be expressed as this. So this V is the same V as we used in the diagonalization of gamma. And delta inverse is just this diagonal matrix and delta transpose. Technically, the determinant of this matrix V can be negative 1 instead of positive 1, but we can always impose that to be positive by swapping the sign of one of the eigenvectors. So we assume this is positive 1. Now, we want to find this integral. Let's name it I0. First, we change the variables from this x to y using this transformation. So V transpose times x. Using this transformation, the Jacobian is this. So the determinant of V transpose, which is 1. So this dy is equal to dx in the integral. Now, using this change of variables, let's look at this part of the integral. So x transpose times gamma times x. If we use the eigenvalue decomposition of this gamma, we have V delta V transpose. Let's group them this and this together. So we have, so x transpose times V is V transpose times x, everything transposed. And this one is just this. So V transpose times x is y. So this is y transpose. So we have this. But this delta is a diagonal matrix. So this product becomes just this single sum. Delta I times yi. Yi is the ith element of this vector y squared. And sum over I running from 1 to n. So in this summation, we don't have any cross terms like y1 times y2 or yi times yj or etc. Because of that, the following calculations become very easy. Here's the calculation. The integral we want to find is now this. So because of the change of variables, we now have y instead of x, and instead of gamma, we have delta here. But this one becomes just this summation, and the exponential of a sum is a product of exponentials. So we can split this exponential function into this product of exponential functions. But since each factor here contains only one variable, we can split this integral into the product of integrals. But this integral is just a univariate Gaussian integral, so the result of this integral becomes square root of 2 pi over delta I. Now, put this product inside the square root. We have 2 pi to the power of n in the numerator and the product of delta i's in the denominator. However, this product is the determinant of gamma, according to the result we have presented before. And 1 over determinant of gamma is the determinant of gamma inverse. So there we have. Next, we calculate the first moment, that is this one. So x times this exponential and integrate it over the entire space. Again, we use this change of variables. Of course, this is equivalent to y equals to v transpose times x. So that is the same change of variables as we have used in the previous result. So using this x becomes vy, and x transpose gamma x becomes y transpose delta times y. So v is just a constant matrix, so we can put this outside of the integral. Now the problem is reduced to calculating this integral. Since this is a vector, let's consider its ith element. So that's this. So yi is the ith element of this vector, and this is this factor decomposed into the product. Now we split this product into two parts, one containing the index I and everything else. But this integral is just 0. So that applies to every element. So this integral eventually becomes the zero vector. And we are done. And finally, let's consider this second moment. So x times x transpose times this exponential integrated over the entire space. Again, we use this change of variables. So using this part, x times x transpose becomes this. Thus, the integral becomes like this. So x times x transpose becomes this, and the exponential factor becomes this as usual. So y transpose delta and y. Now let's put this v outside and v transpose outside. Now we consider this part. So we now take this out as y2 prime as this. Now this y times y transpose, its elements are like this. It's an n by n matrix. We consider the off-diagonal and diagonal elements separately. First consider off-diagonals. So I not equal to j in this ij element. So if we take this element out, so in this matrix we only consider what ij element. And so that becomes yi times yj times this exponential, the same factor here. Now we split this product into two parts, or actually three parts. That is, one containing the index I, and another containing index j, and everything else. So here's the term containing yi, and here's the term containing yj, and everything else is here. But this integral is just the first moment of this Gaussian integral, so this is 0, and this is also 0, so the result is 0. That means all the off-diagonal elements of this integral are 0. Next, let's consider the diagonal elements. In the diagonal elements, we have yi squared times this factor. So again, we split this product into two parts, the one containing the index I, and the other everything else. Everything else is here. So for this part, everything else part, is just a Gaussian integral. It's the zeroth moment. So the result is square root of 2 pi over delta k. Delta k is here. And this one is the second moment of this univariate Gaussian integral. That is square root of 2 pi over delta I times 1 over delta I. So let's put this square root and these square roots together. So we have this product times 1 over delta I. And of course, this part, we have already seen that this is equal to square root of 2 pi to the power of n times the determinant of gamma inverse. So we have this divided by delta I. So the integral, this integral is a diagonal matrix whose diagonal elements are this. And all the diagonal elements share this factor. So the only difference is this part. And the diagonal matrix consisting of 1 over delta 1, 1 over delta 2, and so on is the inverse matrix of delta. So the integral I2 prime becomes this. So this factor times this diagonal matrix, which is the inverse of delta. Now, remember that the inverse of gamma can be expressed as V times delta inverse times V transpose. So the original integral we wanted to find was this, V times I2 prime times V transpose. And this one we have just found, it's this. So this is just a constant. So V times delta inverse times V transpose we have here, which is equal to gamma inverse. So in summary, we have proved these formulas. The zeroth moment becomes this constant. So square root of 2 pi to the power of n times the determinant of gamma inverse. And the first moment is the zero vector, and the second moment is this matrix. So this same constant times the inverse of gamma. Okay, thanks for watching. If you like this video, please hit the like button and please subscribe to this channel. See you later. Bye.